So some terminology that is going to come into play for the rest of the semester are critical values, critical regions, and a non-critical region. All right, so basically what's going to happen is you are going to construct a null and alternative hypothesis. You're going to have an alpha level that is set. Based on that alpha level, then you're going to have to determine what we call a rejection region and a non-rejection region. Those two regions are separated by a boundary, and that boundary is determined by critical values. So the critical values are the numbers or the demarcation points that will separate the rejection region from the non-rejection region. And again, these are found and based off your alpha level, your significant level that you choose. The critical region or the rejection region is a set of numbers or a set of values that if your test statistic falls into the rejection region, then you will reject the null hypothesis. That means that when you compute that test statistic is far enough away from the mean from the null hypothesis to state that there is something going on in the data. So the data will indicate that you will reject the null in favor of the alternative when your test statistic that we will talk about shortly falls into that rejection region. Your non-rejection region or non-critical region is a range of values of the test statistic that indicates the difference between your test statistic and the value under the null hypothesis was probably due to chance, and that there is not really any significant difference between your test statistic value and the value under the null hypothesis. So it's kind of like, where is the demarcation where the cop is going to give you a speeding ticket? So if the speed limit is 65 miles per hour and you're going 67 miles per hour, I'm thinking there's going to be a small probability that you're going to actually get pulled over. But if you're going 80 miles per hour in a 55 miles per hour, I think that the cop is going to say, that's too much. You're going to get a ticket. Right? So there are, when we talk about differences or non-difference, then really kind of what we're talking about, again, is we've come up with this null and alternative hypothesis. And remember, the null is that mu is equal to some value, and your alternative is going to be that mu, say for example, is not going to equal to some value. So you're going to go out and compute a test statistic, right? So if you will, let me get rid of that. If you will, just to kind of set this up a little bit, is you are going to have some value right here of mu naught under the null hypothesis. You're going to go over and you're going to collect some data. And from that data, you're going to compute some summary statistics. So probably one of the things that you're going to compute, since we're working with a mu, well, we already know that our estimator for mu is going to be x bar. So you're going to compute x bar, and here it is. So now the question is this: is the distance between mu under the null hypothesis small enough or large enough than x bar, that if it's large enough, we're going to reject the null in favor of the alternative, and we can conclude that there's something going on in the data that will make the distance between these two large enough that there is a difference. That is, you get the speeding ticket. Or the distance between mu and x bar is going to be small. Now, I think we covered in our previous chapter that we can compute various values for x bar, and of all the values we can compute, they probably are not going to be the same as mu under the null hypothesis. So this difference is just kind of the nature of the beast. So this difference is not a difference because there really is a difference between the two values, but that difference is due to chance. That is, if there really was a difference between these two, then the distance between these two should be large to say that there is a difference. But if the distance between these two is not large, then we're not going to reject the null hypothesis. So the difference between these two is small and is probably just due to some innate random variability that is going on within the data set. Does that make sense? Okay. So to kind of bring things to light, I need to make a couple of assumptions, and I think I can get this. Assumption number one, I want to first assume that the population that we are going to draw from is from a normal distribution. Assumption number two, we are going to assume that the standard deviation for right now is known. And assumption number three, let's just assume that the sample size that we are going to collect is large. So given that case, given the case that we have normal population, we know the standard deviation, and our sample size is large, and our traditional method that we're going to use, or our critical value method that we're going to use, we can use all that normal stuff that we talked about earlier. So the idea now is when I set up my hypothesis testing, remember there's three types of hypothesis tests we can do. Two-tailed, upper-tailed, or a lower-tailed, and all three of those are based off the alternative hypothesis. So if my alternative hypothesis for this one is going to be that mu is not equal to some number, then that means I have a two-tailed test. So that means that, again, putting my number line up here, remember this is mu under the null, and then I have this x bar going on, right? Now please remember, these are standard normal distributions then. So when I go to standardize all of this mu under the null hypothesis over here on this curve is going to go where? Right in the middle, and this value for the standard normal is going to be what? Good, 0, right? So notice here, when I go to standardize x bar then is going to become my test statistic. And just to throw this out, I'm just going to call this z sub ts. When I go to standardize x bar is going to become my test statistic. So my test statistic, if this distance here is going to be small, then when I go to set up my rejection and non-rejection region, if this distance is going to be small, then I would expect the distance from 0 to my test statistic to also be small. So that means that there really is no difference, and my x bar is going to probably fall right here when the distance is small. So that means I am in the do not reject region. Or if the distance between these two is large, then when I go to compute my z test statistic, if the distance is large over here, then the distance is going to be large over here, and that means that my test statistic is going to fall in the rejection region. All right, so when I'm doing a two-tailed test, then if I fall anywhere in the white space, then I fail to reject, and I can conclude that the differences between these two is just due to chance when I fail to reject. If my test statistic falls out in one of these two rejection regions, then there must be something going on in the data informing me that this difference is not due to chance, but there is something happening here. Now, this rejection region and the non-rejection region are separated right here by these two guys, these two boundaries, and these are my critical values. And I will denote these as z sub alpha over 2, a negative z sub alpha over 2, and this critical region here, since it's greater than 0, is z alpha over 2. So that means if I choose a significant level alpha of some value and I'm doing a two-tailed test, then note that this area over here must be an alpha over 2 area, and this area over here must be an alpha over 2 area. Now the other two, kind of a similar argument here, but for this one, let me switch this around. I have my mean under the null hypothesis, and then I can compute my x bar. So again, once I choose my alpha level, then this is my alpha, and this is my boundary or my critical value, z sub alpha. And again, when I go to standardized, mu sub 0 becomes 0, and x bar is going to become my z sub ts, my test statistic. So again, if my test statistic falls in the rejection region, then I reject the null in favor of the alternative. If it falls under here in the non-rejection region, then I fail to reject the null hypothesis. Same argument over here. Okay? So this is kind of the setup right now of where we're at. So at this point, I'm going to pause for tonight. Have a good night.